So today we're going to discuss properties of solids, following up on the previous lesson on properties of liquids. And we will also do a little comparison of the three states of matter, and then we'll look at different kinds of solids. So the main issue with solids is that they're not very interesting. They basically just sit there because, as we've said, you've probably heard this before in other classes, solids hold their shape. They keep the shape of their container, and that's because they are rigid particles that are held in place, and they're held in place by either the IMFs or other forces. And we'll talk about the other forces. We'll talk about the types of forces when we talk about the types of solids in a few minutes. As with solid, liquids and gases, kinetic energy is something that's important. They do have kinetic energy, and because they have kinetic energy, they have to move, but they're being held in place. They vibrate in a fixed position. So essentially, the particles don't move except for to vibrate, go back and forth within a certain position, and come right back to where they started. The speed or the frequency of the vibration increases as the temperature increases, because more kinetic energy gives you more energy to move around. And when we talk about phase changes, we're going to see how increasing that speed and increasing the frequency is actually going to lead to changes in phase. Now, to compare solids to liquids and gases, let's take a look at a table that has all three of them at once. Gases have a lot of space between them. We remember that from kinetic molecular theory. And because of that, they have the lowest density. So we're going to look at the density. Gases have the lowest density. Oh, sorry about that. I have to put that line there because I forget that this doesn't like having things drawn in a table. They have high compressibility, which means you can push them together. We say that they have an indefinite shape and an indefinite volume. You can push them into any shape of any container, and because there's space between them, they can be compressed into any volume. Now, liquids are often thought of as being halfway in between solids and gases, but that's not really true. Their density is high, so they have a high density, almost as high as liquids. It's about 1,000 times higher than a gas. And that's just a rough order of magnitude. Gas is the density is usually given in grams per liter. For liquids, it's grams per milliliter. And because of the milli there, we have 1,000 times higher volume. All right, compressibility. You can almost not compress molecules together or the particles together in a liquid. As you squeeze them, they'll tend to flow rather than compress. We've also said gases have an indefinite shape. It takes the shape of the container. But now, because the particles are close together, they have a definite volume. And if you've ever done any cooking, or if you remember things in lab, you put a liquid into one container, measure it in one container, you pour it into another container, the volume isn't going to change, only the shape. When we get to solids have those particles really close together. So if you look at those particles, they're all really, really close together. You can't get them any closer together. So they have the highest density, with one notable exception, and we'll talk about that exception down below. There is absolutely no way to compress solids together. So if you push them, basically you're going to break them. They have a definite shape, so whatever shape they have, they keep that shape unless you do something like melting them or breaking them. And likewise with volumes, a definite volume. So the important thing about solids is that they form crystals. And this crystal arrangement is an ordered arrangement of the particles. So what do I mean by ordered? I mean that it's a repeating pattern. If you know what the crystal looks like in one area and you move to another area, it should look basically the same. And the particles of those crystals occupy what we call lattice points. And we've heard that term lattice before when we talked about ionic compounds. So lattice points is just what the site is in the crystal that the particles sit on. So there are four basic kinds of solids, four different basic kinds of crystals, and I'm going to take them in order of strength of attraction and melting point, boiling point of the particles. The first is called a molecular solid. Now, these are things that we think about that are gases or liquids, but when they get cold enough, they form solids. So they're solid when cold enough. And this also applies to noble gases, except for helium, of course, which we talked about. Helium can be made into a solid, but you have to put like 10 to 100, I don't remember the exact number, atmospheres of pressure on it. So in this molecular solid, I hope that didn't ruin me. I bet it did. I'm going to keep going. In this molecular solid, we have the molecules are what occupy the lattice sites, or the atoms. And examples of this would be water, carbon dioxide, anything that is a molecule, and they're held together by the weak intermolecular forces that come about due to the partial charges in the crystals. And because those weak intermolecular forces, we have low melting points and boiling points. And these solids are generally pretty soft as well. Now, water is the one exception we talked about up above, where solid is less dense than the liquid. And ice, we know that because ice floats. And the reason ice floats and the reason it's less dense is we have this big open hexagons formed when, if you look very carefully, we've got these hydrogen bonds here. These hydrogen bonds force water into this open structure. The next kind of crystal is called an ionic crystal or ionic solid. And these are going to be ionic compounds where, as you may guess, ions occupy the lattice points. So each point, each sodium and chloride ion is a lattice point. Back in the water, each one of those water molecules is on the lattice point. Examples, sodium chloride, as you see below, calcium bromide, get the formula right, sodium nitrate, anything made up of ions. Here we have ionic bonding. And ionic bonding is particularly strong because we have full charges. So instead of the partial charges, we have the full plus and minus, plus and minus. And because the full charges are stronger, and so they have higher, very high melting points and boiling points. Okay, if we turn the page, or go on to the next page, we now have metallic substances, metallic crystals, in which metal ions occupy the lattice sites, and they're surrounded by that sea of electrons. So this is a copper crystal down below, and each of the copper crystals actually should be a 2+ because it's copper. And what I don't have drawn in here is the electrons. So picture those electrons moving around inside there. And the sea of electrons and the ions, so between the ions and the sea of electrons, we have full charges. I'm not sure why this broke over that line, but that's okay. Full charges, and so that's very strong. Examples, copper, as you see below, sodium, metal, iron. Now, they may all have different exact structures, and you're not responsible for the exact structures, but you do need to know that they do have the metal ions formed on the lattice sites. These bonds are medium strong to very strong. So mercury is medium strong, and we know that because it's a liquid at room temperature. And tungsten, W, is very strong. It has one of the highest melting points of any material known. So metallic bonds have this wide range. I will never ask you to compare the melting points of metallic bonded crystals and ionic bonded solids because they overlap a lot. And because of that range, the boiling points go from medium to very high. Now, the last kind of crystal, we've seen these crystals before. I may have alluded to their properties, but I may not have said anything specific about them. These are network covalent solids. And here we have that word covalent. In these structures, atoms have to occupy the lattice sites. And these atoms are held together by very strong covalent bonds. And because of that, they are very strong, very hard, and strong materials. So down below, you see carbon in the form of diamond. And here, this is basically like a diamond. Here's the diamond. Is like one large molecule. If you wanted to melt diamond, if you wanted to break it apart, you would have to break apart these strong covalent bonds. You notice that each one of those atoms, let me highlight them in a different color. Let's highlight this guy right here. So notice that carbon atom right there is surrounded in a tetrahedral arrangement to 4 other carbon atoms. And this goes on throughout the entire structure. So 4 other carbon atoms tetrahedrally bonded. This is a very rigid and very strong structure. And so it holds together very tightly, and it takes a lot of energy to break it apart. Some examples, carbon, and that's both diamond and graphite. Graphite has a slightly different structure. It also has a high melting point and boiling point. Let's write that in there, very high melting point and boiling point, because it takes a lot of energy to break the covalent bonds. Other examples, silicon and germanium, those are both in the same column as carbon, so they have the same structure. And an unusual one, which we'll talk a little bit more about in a moment, SiO2, which is called quartz. And so that's a mineral that shows up in a fair number of gemstones, and in its pure form, it's a colorless crystal. So those are the 4 types of solids. What we're going to do here is compare the relative strengths. Oh, I forgot to turn off spell check. Relative strengths. It caught me on a spelling error. There should be an S in dispersion. Oh, I'm on my... There we go. Dispersion. There it is. So this is just a table showing the relative strengths of the various types of materials and some examples, going from lowest to highest. So dispersion forces, dipole, and hydrogen bonding. You notice the melting points as we come down, going down here. Melting points and boiling points are going higher and higher. Likewise here. So from dispersion to dipole to hydrogen bonding, we're getting stronger intermolecular forces. When we get to metallic aluminum, it's a very strong force and a very high melting point. Something like lithium fluoride has even higher melting point. And then carbon, the network covalent carbon, has a melting point over 3 times higher than that of lithium fluoride. So very hard to break it apart, very strong. The last kind of solid I want to talk about is an unusual solid, but we see it a lot, and that's what's called an amorphous solid. So the prefix a is a Greek prefix that means without, and morph, you've heard that word morph before. Morph just means shape. So this is something that has no shape, and they are not crystals because they lack the long-range order. In fact, they have a high disorder. There are no repeating patterns. And there's no definite melting point. Instead of melting as you heat them up, they soften over a temperature range. And one big example of an amorphous solid is amorphous silica, which is known as glass. Other examples, rubber, plastic. So these are things that we think of as soft and flexible. So soft and flexible because they are above the softening temperature. And in fact, you can take like a rubber ball and put it into liquid nitrogen, cool it off, and it will become hard and rigid and it will shatter. And as I said up above, glass, which is amorphous, SiO2, silicon dioxide, otherwise known as silica. All right, so this is our look at properties of solids, and I hope everything is going well for you.